push this down here someplace. There we go. The situation that we have is the sun is radiating, and at Earth's orbit, we have the flux of 1,400 watts per meter squared of energy. So clearly the total energy output from the sun is simply the flux at this surface times the surface area, right? So let's calculate that. Energy total from the sun is going to be the solar flux times the area. Of course, the solar flux is given the area needs to be calculated, and the area of a sphere is 4 pi r squared. Several of you asked that question because you wanted to make sure, and that's certainly perfectly okay. So the total energy output, which is going to be 1,400 watts per meter squared, times 4 pi times the radius of 1.5 times 10 to the 11 meters squared. Please check this number. Of course, the meters squared are gone, and we'll have the total output in watts. I get 3.96 times 10 to the 26. 3.96 10 to the 26 watts is the solar output.
Yes.
Okay, so did I get agreement on that one? Okay, good. Well, ladies and gentlemen, the energy comes from the loss in mass. So E total is going to be m naught c squared. That's all we have to do. So, in fact, on my paper I wrote it as delta m, since it was a loss. So why don't we do it the same way here? Delta m c squared. So that's the mass that's lost. Go ahead.
Isn't the energy total mc squared, not m naught c squared?
I wrote m naught c squared because this is mass being converted into energy, not mass being accelerated. When mass is accelerated, then you get the m. But then I changed it here because all I'm talking about is a change in mass, how much mass is lost. So it's very simple then. Delta m is going to be E total divided by c squared. And I am looking for 3.96 times 10 to the 26 watts, which is a joule per second, which is a kg meter squared per second squared per second. Oops. 26 watts is joules per second. We don't put that on there because if it's 3.96 times 10 to the 26 watts joules per second, and we're asking about 1 second. So you lose this many joules in a second, divided by c squared, which is 9 times 10 to the 16 meters squared per second squared. And obviously, but I do want to see the units work out. And I got a simple 4.4 times 10 to the 9. Would you check that, please? 4.4 10 to the 9 kgs. Had you left the per second, it would still come out kgs per second. So the sun is converting 4.4 billion kilograms of mass into energy every second. That sounds like a lot, doesn't it? So for the fun of it, I said to myself, how long would the sun last if it continued this output until it used up all of its mass. Of course, it's not going to do that. But just to get a feeling for how much mass is this, let's convert the entire sun into energy at this rate and find out how long it's going to last. So the mass of the sun, what I'm going to do now is just find out what happens when I use the mass of the sun and divide it by this rate. So the mass of the sun is 2 times 10 to the 30 kgs. And let's say we're using it up at a rate of 4.4 times 10 to the 9th kgs per second. If we're going to use the entire sun at this rate, how many seconds of life? I get 4.5 times 10 to the 20 seconds. Okay, what does that mean? So the next thing I did was to figure out 4.5 times 10 to the 20 seconds divided by what? What did I do? I did years. So I get 3,600 seconds per hour, 24 hours per day, 365 days per year, and of course, I end up with hours are gone, days are gone, and we end up with 1 over 1 over years. So this is the number of years that the thing would last. Check me out. I get 14 times 10 to the 12. 14 times 10 to the 12 years. That's how long it would take to use up the entire sun, converting it into energy. Well, that's interesting. I did one more thing. Look at this. 14 times 10 to the 12 years divided by 13.7 times 10 to the 9th years. Does anybody recognize that number? That's how long the universe has been in existence. So I said 13.7 times 10 to the 9th years per Big Bang. That's how long the universe has been around. So this number will represent a Big Bang. So if we do this division, I get what do I get? Oh, I get approximately 1, obviously 13.7 into 4 is 1 approximately. 1 times 10 to the 3rd Big Bangs. So 1,000 Big Bangs. So when you first look at this number and you say, gee, that seems like a lot of mass that we're converting into energy. Yeah, if you convert the entire sun into energy, it would live for 1,000 times longer than the universe has been in existence already. It would live for 1,000 Big Bangs. So, according to you and me, if I compare this mass to my mass, yeah, it seems big. But when I compare it to the mass of the sun, I find out that's a trivial amount of mass being disintegrated each second. Trivial. So I did that just for the fun of it. When I was done, I thought to myself, what does this mean? What does this number mean? So I fooled around with the number a little bit, just to find out what was going on. Any questions? Yes?
That doesn't take into account the relative velocity of the Earth to the Sun, right?
Correct. The relative velocity of the Earth to the Sun is also trivial. But we're not talking about converting the mass of the Earth. We're talking about converting the mass of the Sun, which from our picture, that perspective, the Sun is stationary.
The one we figured out would be the mass converted from Earth's frame. Is that correct?
From the Earth's frame or from any frame moving so slow as to be trivial. Yes. Website there?
First one says it can't be found.
Oh dear, we could be in serious trouble.
And the other one, I checked the other little perspective, the same thing.
Okay. Yeah.
For R, did you use the radius of the sun or did you?
If you use the radius of the sun, then you better use the flux over the solar surface.
Okay, so you use the radius of the.
Use the radius of the Earth because we have the flux at Earth's position.
Okay, so of the orbit.
Of the Earth at its orbit, yeah. So I'm imagining this giant sphere around the sun whose radius is Earth's orbital radius. Thanks for checking. That means I don't know what to do for lab today, except to challenge you to see if you can find the new website for the photoelectric effect. So all you need to do is start searching. Maybe you can Google it or something like that. But there's an interactive experiment for the photoelectric effect. We don't have the equipment, and I guarantee you we're not going to buy it at the price of the photoelectric effect. We're not going to buy it. So we're going to have to do a computer lab. And let me offer as your first incentive 5 points for finding.
I found it.
He's got it, sorry. Is it the same website?
No, I just Googled photoelectric effect simulator as the first one.
Okay.
Okay, he had a head start, that's not fair.
Thank you very much. Yeah, he gets 5 points for that. Would you do me a favor and copy down the website so we can give it to everybody? But meanwhile, let's get started talking about the photoelectric effect because it's going to form the core of what we're going to talk about for the next few days. So this week's lab is the photoelectric effect. It is an interactive lab on the computer, and Jason will be getting the address for it. But meanwhile, I want to start talking about this effect because it really is the core of what we will be doing for the next few days. First, as a reminder, 1864, James Clerk Maxwell was the one who verified that light is an electromagnetic wave. He did so by showing that the speed of any electromagnetic wave would be given by 1 over mu naught epsilon naught under the square root like that. And I'm going to ask you to do, as a special homework problem, simply demonstrate that this actually comes out to approximately 3 times 10 to the 8th. That part is easy. But then also show that the units work out, meters per second. That actually isn't so easy. The easy part's getting the number. That's the part you love, sticking it in the calculator, right? But that's easy, that's trivial. Show that the units work out. Okay. Then, in 1888, Heinrich Hertz showed that electromagnetic waves actually do exist experimentally. It's interesting to look at his experiment because there's a subtle little part of his experiment that leads to the photoelectric effect. So let's look at Hertz's experiment. What he did was to charge 2 spheres, imagine 2 large metallic spheres like this, and they're being charged with an oscillating generator. So here's a generator of some sort that produces oscillating current, which, by the way, is a relatively high voltage. And what he did was simply to move the spheres together close enough so that a spark will jump each time you are at maximum voltage. So just barely making sparks. He slides the 2 together until they're just barely making sparks. So, use a red. I don't have a red, so I'll use orange. So there's a spark jumping across here every time we reach peak voltage. As a detector, then, he took a bent loop of wire, and I'm simply going to say shaped a little bit like an omega, and put it around the spark. So I'll try to show that, although it's going to be a 2-dimensional picture. So we have this piece of wire going around the spark like this, and showed that as the spark went through this wire, it induced an electric current in the wire, producing a second spark down here. So that was his detector. Okay, kind of an interesting, kind of a basic experiment, but it does show the connection between electric and magnetic fields, because we know it's a changing magnetic field in a loop of wire that induces a current. Well, that then produces another electric spark down here. So here is the core of Hertz's famous experiment. He did notice that when doing this experiment in the presence of ultraviolet light, these sparks jumped more easily. He did not follow up on that. He simply noticed it and he wrote it down. As a good experimentalist does. He just noticed something, wrote it down. He did not follow up, others did. Others began to study this observation in a very interesting way. What they did during his experiments, sparks occurred more readily in the presence of ultraviolet. He did not follow up, others did. So others followed up by doing this kind of an experiment. Let me draw a new experimental apparatus for you, and it will probably be the apparatus that you see in a slightly different schematic when you do the experiment on the computer. It would look something like this. Here we produce two plates. And this comes down to an adjustable resistor attached to a battery. Here I'm going to put in an ammeter. Bring this into the resistor around over to here like that. And I'll measure my voltage across here. Next thing I'm going to do is to surround these two plates with a vacuum. So of course you need a nice glass chamber. I'll try to draw that. Maybe I'll just put it in black also. So there's this glass chamber like this, which is only there to support a vacuum. So let me write down here perhaps vacuum. Now you'll notice that this side is the positive side, and this side over here is the negative side. So we have an electric field across these two plates. But before we talk about that electric field, I'm going to deliberately shine ultraviolet light, UV, on this plate. And what's going to happen is that ultraviolet light is going to free electrons. But you'll notice if you have a freed electron here, or maybe a freed electron there, of course, it's moving, I'm going to call it uphill. It's moving against the electric field because there's positive charge behind it, negative charge in front of it. So these particles are emitted with some kinetic energy like this. They're moving across with some kinetic energy. And if the voltage is too high, the electrons won't make it. They'll come out of the ways and fall back in. But as I lower the voltage, as I move this pointer further and further this way and lower the voltage, eventually the voltage across these two plates won't be enough, and the electrons will actually make it over to that plate. When the kinetic energy of these electrons is greater than the potential energy across those two plates, then the electrons will arrive and they'll show up as an actual current. You can actually read the current. So if the voltage is too high, if at this pointer over here the voltage is too high, none of the electrons are making it, then your ammeter is going to be zero. There's no current. Lower the voltage, lower the voltage, lower the voltage until eventually you get the kinetic energies of the electrons equal to or greater than the potential energy across those two plates, and the current will show up. So we're constantly measuring the voltage and looking for current. This apparatus was used to explore what we now call the photoelectric effect. And at first it doesn't seem very exciting. Why? Because everybody knows that waves carry energy. So the ultraviolet light coming into this plate is bringing energy to that plate. The energy is converted into kinetic energy of electrons. The electrons goes dashing across the plate, no big deal. I often think of it, I call it the Malibu effect. Because it's just like, isn't it just like those poor people that live down in Malibu? You know that every once in a while there's a big storm, the waves get real high, the waves come onto the beach and wash away all of it, scatter the houses, right? So we see that happen all the time in wave theory. Waves carry energy, waves come in and strike the shoreline and the houses there and scatters them. So that doesn't sound very exciting. You say, okay, I expect this to happen. But there are a few subtleties here that I would like to call out to your attention, because it's not until you start doing the experiment that you notice the subtleties. Now let me check my notes here. Electrons emitted, if their kinetic energy gained from the light is enough to climb uphill against the electric field. So I did write, we're looking for the time where the kinetic energy here equals the potential energy here. So the kinetic energy when the electrons are emitted is equal to the potential energy when the electrons strike. So I think you'll agree, if I have it set at just the correct voltage, then the electrons will fly across, just coming to rest when they reach the other plate. That's the point that we're looking for right there. You probably remember what the electric potential energy is. The potential energy is V times Q. QV is the potential energy if you have a charge moving through a voltage. So be kind of cautious now. Remember, we're talking voltages, not velocities. The V is going to represent voltage. Okay, so this is what we're looking for. We're looking for this situation where the kinetic energy is equal to the potential energy when it strikes the negatively charged cathode. Now what I'd like to do is just to show you sort of schematically what the results are when you first start doing the experiment, because there's a small curiosity here. So what I'm going to do is I'm going to plot on the vertical axis the photocurrent. That's the photocurrent on the vertical axis, and the retarding potential, V, on this axis here. So what I'm going to do is I'm going to be measuring the photocurrent. That's this here, photocurrent. That's this measurement here at given voltages. And what I'm going to do is I'm going to illuminate this with one specific color of light. So notice I'm going to say frequency equals nu equals constant. But I will be changing the intensity of the light. It's kind of curious. We start with a dim light perhaps here, and as we do the experiment, we get a result of something like this, and we arrive here at a stopping potential, which I simply call V naught. So this is V naught. So we turn on the light at a certain intensity, and let me just call I the intensity of the light. We turn on the light with a certain intensity, so we're shining light on this thing, and we start raising the voltage. We start moving this thing from over here in this direction like that until we finally stop the photocurrent. And that's where our experiment stops. So we put a point right there. Interesting. Now, double the intensity of the light. We're going to go up here now to twice I. So about here, this is twice I. The only thing that has changed is the intensity of the light. We double the intensity of the light, and immediately the first thing you notice is that you've got double the photocurrent. But what's really curious is watch this. As you start raising the stopping potential, guess what? You end up in exactly the same spot, which says that your new electrons from the second experiment have the same maximum kinetic energy. Do you see how odd that is? Think about the Malibu effect. You know that if you've got a certain size wave that hits a house, it scatters the house with a certain energy. If you double the height of the wave and hit the same house, you're going to scatter with more energy, aren't you? That doesn't happen here. You strike strike the surface with twice the amplitude of wave, and you have the same stopping potential, which means that the emitted electrons are emitted with exactly the same kinetic energy. Just to test it, let's triple. Let's go up one more, about here, and just like before, this is now 3I. If you triple the intensity of the light, you're going to initially triple the photocurrent, but it does just like before. It has the same stopping potential. So, as you increase the intensity of the light, you increase the photocurrent. The photocurrent is dependent upon the intensity of the light, but you are not changing the kinetic energies of the scattered electrons. I don't care how far up or down you go on the intensity side here, you always get the same stopping potential. That seems out of keeping with our understanding of what I just referred to as the Malibu effect. If you're coming with these huge, immense, tall waves, those houses are going to be scattered very energetically, but not the electrons. Something's wrong here. What? Don't know. So kinetic energy does not depend on light intensity. Another interesting thing, this experiment demonstrates no time lag. From the very instant you turn on the light, there's a photocurrent. From the very instant, to within our limits to do the experiment, which at the time was about to within 10 to the minus 9 of a second, within a 1/10 of a second. There's no time lag. And you might be wondering about that. You say, but the speed of light is very fast. That's not the question. Imagine we have a light intensity. We're going to do this experiment now with a very low intensity light. There's some room on the board here, and then we can do a calculation just to show you how this lack of time lag is significant. So imagine that we have a light intensity I, 10 to the minus 6, 10 to the minus 6 watts per meter squared. That's a very dim source of light. And it's striking a sodium surface. Now, by the way, on a sodium surface, if we're going to assume that the light energy is absorbed just by the top layer of atoms, and that's the conservative estimate. So you're shining this light on a square meter of sodium, and only the top layers are absorbing the energy. There are about 10 to the 19 atoms per meter squared. So this light intensity is being spread over 10 to the 19 atoms. Well, what do we have? Look at this. We have 10 to the minus 6 watts per meter squared divided by 10 to the minus 19 atoms per meter squared. And so we end up with, when we flip this thing over, we end up with 10 to the minus, what am I trying to say? 10 to the minus 25, and then we end up in watts per atom. So here's the rate at which each atom is absorbing energy. It's absorbing energy at the rate of 10 to the minus 25 watts per atom. Okay, if you wish, that is 10 to the minus 25 joules per second per atom. That's the rate at which we are absorbing them. Now let's convert that. 10 to the minus 25 joules per second per atom times, where is it? Divide by 1.6 times 10 to the minus 19 joules per electron volt, and you end up with 1 over 1.6. It looks like it should be. Oh, I see what I'm doing. Excuse me. I'm reading my notes in two different directions here. So what I did was I said to myself, well, how long 10 to the minus 25 joules per second times T, how long is it going to take for this thing to absorb the appropriate amount of energy to liberate an electron? And so it turns out that T will equal 1.6 times 10 to the minus 19 joules divided by 10 to the minus 25 joules per second. And that is 1.6, here's where I read it backwards, 1.6 times 10 to the 6 seconds. So what I just did was I just gave one electron volt of energy. How long will it take at this rate? How long will it take for one electron to absorb 1 electron volt's worth of energy? And it's going to take 1.6 times 10 to the 6 seconds, which, by the way, is approximately 18 days. So at this flux on a sodium surface, to give the electrons just 1 electron volt of energy, it's going to take about 18 days. No, as soon as you turn it on, you've got photocurrent. As soon as you turn it on, within a billionth of a second, you've got electrons traveling across. How can that be? That's a major difference. Yes, you agree. Okay, I can tell. Yes. 18 days. Now, also on, my next page is titled Also On. Watch this. We're going to do the experiment again. This time what we're going to do is hold the light intensity constant. So I equals constant. We're going to be measuring across the horizontal axis the same thing, the retarding potential. The vertical axis is photocurrent. Like this. And what we're going to do now is we're going to change the frequency of light. So just like before, if we start out like this, we'll have a photocurrent of something and a retarding potential here. And what happens is, let's now increase the frequency. Go to a higher frequency light. At the same intensity, you start out with the same photocurrent, but when you increase the, this is called nu3. This is nu2. When I increase the when I increase the frequency of the light being used on this photoelectric effect, what I end up with is a higher stopping potential. This is V0 of 3. This is V0 of 2. So as I raise the frequency, obviously the kinetic energy is going up because we have a higher retarding potential. So we're stopping it at a higher retarding potential. We did it a third time. V0 1, nu 1. And we have that frequency 1 is larger than frequency 2 is larger than frequency 3. So what we end up with is, by starting out with the same intensity, we always start with the same photocurrent, as seemed to be implied over here. But what we did was we used ever higher frequency light, and each time we did that, we got a higher stopping potential, which means raise the frequency and you raise the kinetic energy of the electrons when they're first emitted. Again, that seems inconsistent with our story of the Malibu effect. What do I mean by that? It doesn't matter. Down in Malibu, it doesn't matter the frequency with which the waves hit. What matters is the energy in the wave. That's what scatters the house. In this case, it's not the amplitude of the wave, it's the frequency of the wave that seems to determine how much scattering goes on and how energetic the scattering is. So the scattering energy seems to be related to frequency, not intensity. And that's really strange. Finally, to actually put this all to work, let's do one last experiment. Our last experiment is like this. Vertical axis is going to be maximum photo energy. Essentially selecting this point, the maximum photo energy across the vertical axis. The The horizontal axis is going to be frequency, nu, and we're going to do, first we're going to do one experiment, and we're going to discover that with one experiment like this, actually using cesium, we get a nice straight line like this. This is supposed to be a straight line right down here to what I'm going to call nu naught cesium. So it's a nice linear relationship. If you start measuring the photocurrent's maximum energy, that is the threshold voltage there or here, the threshold voltage on either spot, then you discover that below a certain frequency, you never ever scatter electrons. No scattering of electrons below this particular frequency. But if you go above that frequency, you get a nice linear relationship. It's a nice straight line. Well, that's interesting. Let's try a different surface. What was the next one? Sodium. And guess what? You get almost the same thing, except look. It's been shifted a little bit. It has the same slope. This was sodium. And this then would be nu naught for sodium, like that. We get another, let's do one more and see if it still works. Calcium. Calcium was way down here, actually. But same thing. We get nu naught for calcium. So to be able to start to figure out what's going on, we do this experiment and we discover that there's a linear relationship between the frequency of the light being used and the energy of the emitted electrons. However, it does not go through the origin, and each particular surface has its own unique threshold frequency from which the light is emitted. Well, the first thing you do is you curve fit, right? We don't have an explanation yet. We've noticed all these curious things. This relationship, this time lag, this relationship, all quite curious, but we don't have an explanation yet. Well, the first thing you do is you just simply curve fit this thing. You try to explain it by curve fitting it. And it's really easy to do because you've all taken that class, right? It's just a straight line, not through the origin, so all you have to do is to write down that the kinetic energy of the scattered electrons is equal to, and it's the slope times, and notice here I put nu minus nu naught. And how do I know to do it exactly like that? Yeah, you shifted it, you moved it back to the origin, because it seems to have been shifted nu forward, so you move it back that same amount. Yes, now we have a nice little relationship. By the way, of course, the slope, very nicely for all the experiments, the slope is always the same. If you work it out, the vertical axis, of course, rise over run. The vertical axis is energy, and the horizontal axis is frequency. So you end up with the slope. First thing I'm going to say is delta kinetic energy divided by delta nu is going to be joules over hertz, which of course is joules times seconds. So the units are going to be joules times seconds. If you measure the slope very, very accurately, you find out that the slope, which we are going to call h, is equal to 6.63 times 10 to the minus 34 joules seconds. Would you find out what that is equal to in EV seconds? Just convert it now. You have the conversion factor, you've got the slope, just do the conversion and then look up and see if you get the number I got. Times 10 to the minus 15 EV seconds. Okay, you can use the slope either way, depending on which set of units you're working in. Joules, if it's a high energy experiment, or electron volts if it's a low energy experiment? Well, now we have a very nice thing. Kinetic energy, maximum. Remember, we're talking about the maximum kinetic energy is the retarding potential, is going to equal h nu minus h nu naught. So all I did was multiply in there, you see, is h times nu minus nu naught. And I did that for a very specific reason. What's very exciting about this is that it relates to something that was going on 5 years earlier. Now that we're done with the math, let's take a couple of minutes and talk about the physics. The physics to me is the really interesting part. Anybody can do the math. But the physics is the interesting part. This photoelectric effect was first noticed by Hertz 1888, but he didn't follow up. Shortly thereafter, in the 1890s, people were doing the experiment and coming up with these strange results, no time lag, that the scattering energy of the electrons seems to be related to the frequency of the light and not the intensity of the light. And that there is a threshold frequency below which no scattering ever takes place, no matter how long you wait. There's all these mysteries going on. That's happening in the photoelectric world. So for about 10 or so years, people are doing the experiments with no explanation. Meanwhile, over in a different world over here, and we've actually already mentioned this, in 1900, Max Planck is trying to figure out black body radiation. That's a whole different world. Photoelectric effect over here, Planck and his black body radiation is over there. And he discovered, do you recall, he discovered with two postulates he could actually explain black body radiation. Do you recall what the two postulates were? Number one, easy to buy. He had to assume that atoms and molecules existed. It was that second postulate that seemed so puzzling, and that is that atoms and molecules are diminutive, discrete electromagnetic oscillators. It means that they oscillate with one frequency and then they jump to another frequency or they jump to a lower frequency. They do not change in a continuous fashion, but in little jumps. That seemed quite odd, but his mathematics fit the experiment perfectly. Planck said, for some reason, I don't know what it is, these little electromagnetic oscillators jump from one frequency to another, but they emit light in a continuous fashion. Now, why did he say that? Because the support for electromagnetic radiation, both the experimental, Young's experiment, and the theoretical, Maxwell's theoretical work, both of those so beautifully describe and support the notion of electromagnetic radiation that even Max Planck said, well, electromagnetic waves have to be these nice continuous waves just like you surfers enjoy out there on the ocean. So Planck was the first one to come up with the idea that there was quantized energy jumps, but it made him very uncomfortable, and he said, that seems to be a theoretical thing, but I believe that the electromagnetic radiation was continuous. 5 years beyond that, 1905, now Einstein is looking at all of these different things. He's looking at the photoelectric effect, a deep mystery. He's looking at the ancient theory of light being made of continuous waves, and he's looking at Planck's discovery of quantum oscillators. And he said, you know what I think? If you look at all of these pieces together, he says, you know what I think? I think that this equation is telling us that Planck's basic idea of quantum oscillators implies that light is produced in little bursts. Not as a continuous wave, but in little bursts. He said there's more to Planck's idea than Planck even knew himself. He said, I think what we're talking about here is that the energy emitted in light is going to be given by h nu, guided by these two things. So when you have a burst of light released from one of these little quantum oscillators, it makes a little burst of energy which is tied directly to and only tied to the frequency of the light. So this little quantum of light we will call the photon. We give it that special name because it has a very unique interpretation. A photon is a wave-particle duality. It has characteristics of both. Because it says, look, this is what's happening. Here is the energy being carried into the photoelectric effect as the photons of the ultraviolet light coming in. It takes a certain amount of energy, and we're over here at the threshold energy. We're talking, it takes a certain amount of energy to pull the electron out. We will call that the work function, because the electron, of course, is stuck into the surface. You come in and you smack that thing with a billiard ball type collision, and some of this incoming energy is used to liberate the electron, and the rest of it is given as kinetic energy to the electron. So the kinetic energy of the liberated electron is going to equal, well, here's the total incoming energy, this is how much work you have to do to liberate the electron, whatever's left is the kinetic energy. 1905, Albert Einstein was the one who realized that Planck's initial guess 5 years earlier strongly suggested that light has this strange dual personality, which we now will call the photon. It has particle and wave characteristics. And the real departure is the energy of the photon is directly tied to the frequency of the photon only. Well, ladies and gentlemen, that worked. That's how the photoelectric effect was first understood. This is, of course, one of 3 papers that Einstein wrote in 1905. I find it interesting. Last week we were discussing special relativity. That was one of the papers released in 1905. The description of the photoelectric effect, utterly different topic, also released in 1905. The last paper is a paper on something called Brownian motion. We will talk about that. Any one of those papers would have been sufficient to secure Einstein's place in history as absolute genius. And yet, working at a full-time job as a patent clerk, starting and raising a family, in 1 year he writes 3, not 1 papers. And so everybody refers to 1905 as Einstein's miracle year. That was when the miracle happened. Well, now we can understand what's going on. So I have a real quick in-class problem, which will rely on looking up. Somebody find, please, remember the last cover of your book? There's a list of charted information. Find the table for the work function. Okay. Time shrinks.